Hello again and welcome. Today we're going to be looking at the UNI-T UT33A. The last meter I looked at was this UT125C. This meter was damaged with a 5,000 volt peak transient. Again, that was derived with our transient generator. That's pretty good for a UNI-T product. I'm kind of curious how well this meter is going to perform. This meter is a 2000 count. You can see it does come with a little pamphlet. Unfortunately, it's not in English. One of the nice things about this particular meter over the previous one, you notice that this one uses standard test leads. They did provide a set. This is what they look like. Unfortunately, you can see it does not power up, and they did not supply batteries with this particular meter. Let's just have a look. Looks like we just have to remove the one screw, and it takes a couple of AAAs. So this is a fresh set of nickel metal hydrides. First thing you notice, the battery indicator is on. Of course, the voltage coming off these batteries is a little low, but it is something you may want to consider if you buy a meter like this. Alright, let's just use our test box here. We're going to run through a basic functional test. And we'll start with the AC volts. This should be 2.5 volts AC. That is correct. This is at 60 Hertz. This is with it being DC biased. This is at 30 Hertz. Here's 15. Here's 120. This should give us roughly 70 volts. You can see it's a little bit low. Let's try it on DC. This should give us roughly 60 volts. Good enough. Let's try it with our 5 volt reference. Very good. This should give us roughly 115 millivolts. Looks good. Let's try it in resistance. Here's with a short. Wow, it is slow. Alright, let's just try it with a 1 ohm resistor. Looks good. This is at 50 ohms. That's good. Here's 100. It's good. Here's a 1K. This is a 10K. This is a 100K. A 1 meg. A 10 meg. Here's a 40 meg. This is a 100 meg. This is a 1 giga ohm. You can see it over ranges. Continuity mode is fast. You can see it's a non-latching type. Let's go to diode check mode. And here is a single silicon diode. Here's 2 in series. This is a white LED. It cannot light that up. Let's just try capacitance. If I hit rel, does it zero it out? Looks like it does. This is a 150 picofarads. Looks good. This will be a 0.1 microfarad. Looks good. This is a 1 nanofarad. Looks good. This is a 1 microfarad. Spot on. Here's a 10 mic. And here's a 100 mic. Alright, so our meter appears to be functional. So one of the things that I don't like about this particular meter is they share the input jack with the current. We can go ahead and test this real quick. So this is going to be 100 microamps. Fairly accurate. Here it is with 10, and here it is with 1 microamp. Again, this is the milliamp setting, and this is 100 microamps. So it looks like the current input works fine. Again, I don't typically do anything with these meters with the current. Unfortunately, the problem with these is these are going to be fused. So what we're going to have to do is pull out that fuse Don't remember if there was a screw underneath these or not. Doesn't look like there was. So I think all you have to do is remove these two screws here. So just the two bottom screws have to come out. And this is what the meter looks like on the inside. You can see they are using a ceramic type fuse. I assume that these are sand filled. You can see there really isn't a whole lot to this meter. Here's our input jack. You can see it goes straight into a PTC, and you can see there are no MOVs. Looks like there's a couple of transistors here that are making up one of the clamps. Maybe there's another clamp up here. What I'll do is just pop this out real quick. Let's go ahead and put our batteries back in. And let's just make sure that the meter will function without that fuse in there. So here we are in AC volts. Again, this should be roughly 70, and you can see it is reading the voltage correctly. Let's try it with DC volts. Again, this will be our 5-volt DC reference. That looks fine. Again, this should be about 115 millivolts. That's correct. Let's just try it in resistance real fast. So here's with a 1K ohm resistor. And that is correct. Let's try it with continuity. That's fine. Diode check. We'll just short the leads. That looks good. And let's try it with a capacitor. Again, this will be a 1 nanofarad part, and that is correct as well. So what I'm going to do is leave the fuse out for the duration of our transient testing. That way we don't blow it. Okay, so I've got my ESD gun out. We're going to be using this as a DC power supply. Just place the meter in its DC volt mode. You can see this meter is Cat 2 600 volt rated, and it looks like it can read a maximum of 600 volts. Alright, let's start turning it up a little bit. Here's 200. Here is 500. And sure enough, it starts to beep. It's 600 volts. Let's just go up a little higher. Yep, and it just overranges. So it appears that the meter will handle the input voltage that they specify. Not too surprising, 600 volts isn't very high. We'll just get right into our testing. First thing we're going to do is our AC line test. Again, this generator puts out a full rectified 220 volt signal. You can see we're reading 120 volts. That is correct. What I'm going to do now is just rotate this through the different settings, and let's see if we damage the meter. That's correct. Alright, I'll just run through a quick functional test. The UT33A survived that test just fine. Next we'll be performing our grill starter test. This is typically what damages the UNI-T meters. Again, we're going to be applying 5 transients, both positive and negative, with the meter set to each mode, and then we'll functional test it. Again, we'll flip the leads around to run the transient in the opposite polarity. You can see it's obviously having an effect on it. Alright, let's just, for a quick sanity check, we'll go to resistance. Notice it still reads an open. Meter's probably okay. I'll go ahead and run a full functional test on it. Alright, the UT33A survived that test just fine. That's pretty amazing because, again, that grill starter has damaged an awful lot of UNI-T products. I'm starting to wonder if they've changed their stance on robustness. It really is too bad that UT181A, which is basically their highest end meter that they offer, is so susceptible to static discharge. Alright, so what I've got here is my homemade ESD gun. Again, you've seen this before. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Alright, that's it. We'll go ahead and functional test the meter. Again, let's just check it in resistance real quick. And you can see it is not reading a low resistance. That means so again, there's a very good chance that we did not damage the meter. I'll go ahead and functional test it. So the UT33A Plus survived that test just fine. Next, we'll be using the transient generator to apply a 1000 volt peak signal into the input of the meter. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. These transients are going to have a 100 microsecond full width half height, and the generator's source impedance is 2 ohms. So it's a little different than the IEC standard. Again, this is not a combo generator, so don't confuse my testing with the IEC standards. This is not a safety test. Again, this transient generator is limited to about 20 joules at the most. Alright, so here we go. And we'll flip the leads to change the polarity. That's going to be annoying. And that's it. We'll go ahead and functional test the meter. Alright, the UT33A Plus survived that test just fine. I've reprogrammed our generator for 1.5 kV. Again, this will be a 100 microsecond full width half height, 2 ohm source impedance. And we'll be applying 5 transients, both positive and negative, with the meter set to each mode. That's it. The meter passes functional test. I've reprogrammed our generator for 2000 volts peak, 100 microsecond full width half height, again with a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. That's it. Our meter survived the 2000 volt peak test. I've reprogrammed our generator for 2,500 volts peak, again a 100 microsecond full width half height, and a 2 ohm source impedance. And we'll be applying 5 transients, both positive and negative, with the meter set to each mode. And that's it. UT33A Plus survived that test just fine. Again, that was 2,500 volts peak with a 100 microsecond full width half height and a 2 ohm source impedance. I've reprogrammed our generator for 3,000 volts peak. Again, we'll be applying 5 transients, positive and negative, to each mode of the meter. Okay, that was 3000 volts peak. Let's just do a quick sanity check. Looks like the meter is probably okay. We'll go ahead and do a functional test. Alright, the UT33A Plus survived that test just fine. I've reprogrammed our generator for a 4000 volt peak. Again, a 100 microsecond full width half height and a 2 ohm source impedance. We'll be applying 5 transients with the meter set to each mode. And here we go. Again, for those of you not aware, I don't believe that the UT139C survived this test. I think it was damaged somewhere around 3000 volts. This UT125C was damaged at 5 kV, so it did not survive the maximum voltage that's available from this transient generator. Oh, I just heard her break down. Alright. Yep. It's totally dead. It's not coming back. I think that we've damaged the main controller IC. Okay, let's just have a look. So again, that was a 4000 volt peak transient. Let's just see if pulling the battery will reset it. Does not appear to. Yeah, I bet you we've damaged the main controller IC. Let's just see if we can see any damage. I believe we just have to remove these 3 screws. Yep. So here's what our switches look like. You can see the board was greased. You know, I don't see any damage to the PTC. So yeah, no visible signs of any damage at all. I'll tell you what, for fun, seeing that the meter is already damaged, let's just put this back into the case. Let's connect it back up to our transient generator, and we'll run this thing with the case off. Maybe we can tell where it's breaking down at. We'll bring the camera in a little closer. Alright, again, this will be 4000 volts with the meter set to its millivolt range. Let's just see if we can see where this thing is breaking down at. Ooh. Yep. You can see right down in here and up in here. Right across the 2 resistors maybe. So you can see, looking at the circuit board, there really isn't a whole lot of damage. So for this one last test, I've changed our test leads out, and I've gone ahead and attached our low voltage generator. So again, the low voltage generator, it's limited to about 600 joules, not a lot of energy. I call it a half cycle line simulator. It's basically putting out the amount of energy that would be available for a half of an AC line cycle. Typically the meters will sustain quite a bit more damage when I use this generator. So I've got my high-speed camera out. Okay. To take our chicken stick and we'll strap out our generator. Both these generators could actually be lethal, but this top one especially, it's not something that you want to mess with. Alright, everything is strapped short. Let's go ahead and we'll disconnect our meter real quick. You can see there's a little bit of damage up in this area right here. Looks like this trace here got hot. Certainly this area here got hot. You can see this resistor has been damaged. Also notice down here though, there's some additional damage. Let's just pop this thing out of the case again real quick. Let's see what the back side of the circuit board looks like. Oh, yep. You can see the soot. Let's have a look underneath our display. I wouldn't be surprised if there's not some additional damage to the circuit board in that area as well. And notice on the bottom of the lens, yep, you can see right along here. See that discoloration? Oh yeah. Look at that. There you go. That's a set of Pace micro tweezers with an ST50 base. I do like having those sitting at home, I'll tell you. I bought those a few years ago and really enjoy having those around. Anyway, you can see the damage. Again, that's only about 600 joules. Nothing like what you'd see on an AC line. And of course with the AC line, it's going to be sustained. So this is a fairly controlled environment that we're using. But like I say, still potentially lethal. So I have to be careful when running these tests. You do wonder what would happen if we actually ran this across the safety test. Would the case stay intact? I don't know. Well, that concludes our testing. Looks like the UT33A Plus survived all the way up to 3000 volts and was damaged at 4000 volts peak with a 100 microsecond full with half height and a 2 ohm source impedance. Again, that was a positive transient. I just want to mention that these last two meters that I looked at, this UT125C as well as the 33A, again, both of these meters surviving our high voltage transient testing, which is what damaged the UT181A. Again, this meter was damaged with the first hit of the grill starter. It has been repaired. To me, it's just sad that it's not even as robust as what these cheap $50 meters are. This could have been a very good meter. Some people have talked about them revising this. I'm not sure if they ever have or not. I can tell you that the components that they used with this were quite good. So this meter could have been improved with a little bit more engineering. I don't know. Maybe UNI-T is paying attention and they're trying to make more robust meters now. It'd be nice. Well, that's going to be all for this video. Hopefully you enjoyed it. Till the next video, we'll see you then. Later.